This is version A for decision 2017. So it's using the data sheet for building a rockery. As you can see here, this is an alphabetical order. However, by the time it gets into a question, it'll be written in the order you need to do the tasks. First off, these will be done in approximately this order, in as much as you won't be asked to do something lower down before you do something higher up. The precedence or the immediate predecessor is what you have to wait for. So in order to bring the topsoil onto site, you need to have ordered the topsoil, and from my point of view, you need to have removed the grass from that area, because otherwise it will die underneath the topsoil. So these durations tell you how long something's going to take. People will normally do the whole of A, B and C actually in a single diagram. So for an activity network for the work involved, just from a practical point of view, trying to keep this fairly neat. First off, we've got A, and that doesn't take anything before it. Then looking at B, we are removing the grass, and that doesn't have anything that happens first. Then C, we are ordering our topsoil, doesn't have anything that happens first. Then we get to D. Now D has to wait for both B and C. So if we put D over here, and this is going to wait for these two. E has to wait for C, but doesn't have to wait for anything else. So E is only going to have to come outside of C. F, fitting a pond base, has to wait for E. G is going to have to wait for both A and E. So if we put that up there somewhere, so it's still going in the right direction, we're not going back on ourselves. H, filling the pond with water, is going to come after F. And then I is going to come after both D and G. And that's all we actually need to do to finish. So we are going to have to end. So if we start off, then we've constructed our activity network, so that's our first 3 marks. Earliest start times for each activity. What we're looking at doing here is finding out what is effectively going in the first box each time. So just before we do that, A is going to take 0.5 to do. B has a duration of 3. C has a duration of 0.5. D has a duration of 1. E has a duration of 5. F is going to have a duration of 2. Then G has a duration of 1 and H is at 2 and I is at 1. We're now in a position that we can actually start filling this in. So if we think about when things can start, first off, if we look at A first, A can start at 0, nothing happens first, nothing happens first, nothing happens first. D has to wait for both B and C to finish. So B starts at 0, takes 3, so we'll finish at 3. C starts at 0, finishes after half an hour. So if you're waiting for something for 3 hours and for something for half an hour, you're going to be waiting for the one that takes 3 hours to finish, as that will finish more slowly. E is just waiting for the 0.5. F, E starts at 0.5 and takes 5, so that's going to finish at 5.5. H is going to finish at 7.5. So again, E, 0.5 and 5 is going to finish at 5.5, and that's far slower than this at just half an hour. So going into I, we are waiting for this one to finish at 4 and this one to finish at 6:30. So the one we actually end up waiting for is the 6:30 one. So this would take us to 7:30, whereas this one would take us to 9:30. When we're working backwards, it works in a similar way, only because we're doing deadlines, we have to go for the earliest deadline so that we're not keeping somebody else waiting. So we're finishing at 9.5 in both of those cases. So for here, if this one's got to finish at 9.5 and it's going to take 2 hours, then the deadline that they have to give is going to be 7.5. For here, the deadline that these are going to give, they're going to need stuff ready to finish at 9.5. They take an hour to work, so they're going to have a request that goes to these two at 8.5, so that they've got enough time to do their 1 hour's work. Then we're going back to E. So E is given a deadline from F of 7.5 take away 2 at 5.5. This one's 8.5 take away 1. So the deadline this one's going to get given is 5.5. A, this has to be finished at 8.5. It's going to take an hour's work, so deadline for needing their stuff is going to be 7.5. The deadline here also is going to be 7.5. And this one's given 2 deadlines. One deadline is going to be 7.5, the other is going to be 5.5 take 5, which is 0.5. So the deadline they've actually got to work to is 0.5. The critical activities, those are the ones where we don't have any freedom. So here you've got 0.5 is 0.5. That's true, so that's critical. 0.5 plus 5 is 5.5, so that's critical. 5.5 plus 2 is 7.5, so that's critical. 7.5 plus 2 is 9.5, so that's critical. What you'll notice is if nothing else branches in or out, then everything else in that remaining section is also going to be critical. Whereas when we're up here, 3 plus 1 isn't 8.5, 6.5 plus 1 isn't 9.5, 0 plus 3 is definitely not 7.5. So our critical activities They are C, E, F and H. They're often phrased as critical activities because it's not always a path. You may have bits where it's doubled up. Section B. This question is or has come from the section on Florence. We've utilised part of the map and we've utilised the table to get the distances on there. We are using Dijkstra's algorithm and we are doing walking time in minutes. We are asked to find the shortest walking time from PP to GA and to show all the temporary labels and state the route. So we are going to GA and we are coming from PP. So if we start at PP, Dijkstra is looking at boxes. So we start with a 0 and then we get into the algorithm itself. So box the smallest thing that doesn't have a box around it already, and then do one step in each direction. So from 0 we've got a step of 4, we've got a step of 10 and we've got a step of 5. Then we repeat. Box the smallest thing that does not have a box around it, that will be 4. One step in each direction. Add 3 gets us to 7. 4 add 6 gets us to 10, but there's already one there. And 4 plus 5 gets us to 9. There's already an option of 5 there. 9's bigger, so we'll leave with what we've got. Box the smallest thing that does not have something round it, that's this 5 over here. So 5 plus 10 is 15, so which is bigger than the 10, so we leave it and we can't go anywhere else. Then we box the smallest thing that does not have a box round it, which is that 7. So from here we could go up here, which would give us 18, which is bigger. We could go up here, which is going to give us 14. We could go along here, which will give us 15. Then we box the smallest thing we've got. So that's this 10 up here. So one step in each direction. 10 gives us 19. 7 gives us 17. 9 gives us 19, 8 gives us 18, but we've already got a 14, so we'll stick with the 14. Then we box the smallest thing that doesn't have a box around it, which is 14. So 14 plus 3 is 17. Now 17 is a better option than 19, so we neatly cross out 19 and write 17. We've then got 14 plus 8, bigger than 15. 14 plus 9, bigger than 17. And then we're done. So box the next thing that doesn't have, the next smallest thing that doesn't have a box around it. So we've got 15 plus 7, that's going to be bigger. 15 plus 14 is going to be 29. And that's about it. Okay, so the next smallest thing that does not have a box around it. We could choose either of the 17s, it really doesn't matter. So this 17, one step this way gives us 18. So cross through the 29, make sure it stays legible because that's what they're talking about with the temporary labels that they ask us to show. 17 plus 14 is going to give us 31 up here. So we now actually have an option of how far it could take us to get there at 31, but that's unlikely to be our best option. 17 at 9 we've done, and all sorted. Okay, this 17, we do need to box it because it's the smallest thing that's not been boxed, but we don't have to go anywhere because 17 plus 8 is bigger than 18. The next smallest thing that we've got is this 18. So we've got 18 plus 15. So that should mean we can cross out the 31 and then write in 23. And we can't go anywhere else that's useful. Right, the next smallest thing is this 19. So from here, 19 plus 10 is 29, and that's bigger. That's rubbish. 18 plus 15 is not 23, it's 33, so we would have kept that 31. Then we've got 19 plus 10, so we'd cross the 31 out nicely and write it as 29. The only thing we've got left to box is this 29, so that tells us that the distance for the shortest walking time is going to be 29 minutes. And the way we got there is a bit where the adding up makes sense. So 29 minus 15, not 18. 29 minus 10 is 19. So we will have come from GA and then gone to LB. From LB, 19 minus 9 is 10, so we came from SP. Now we've got two options here because 10 minus 10 is 0, but also 10 minus 6 is 4 and 4 minus 4 is 0. So either of those two options is absolutely fine, but we may as well go the more direct route. So our route for going from PP to AG is up here. So we have our route, we have our time, and that is the full 6 marks because we've got everything we need to boxed and we've got evidence of the crossing out. Section C is also on Florence. So we are told that we are looking at some places in Florence. We are told that it is again walking time in minutes. And in this case, we are also told, very subtly, the total time for all of the roads. This is a useful piece of information. It means we don't have to add everything up. So, questions. He wants to collect and leave at one place. So this is a situation of start and finish at the same point. So that's the same start and finish. And what we are doing is a Chinese postman. So Chinese postman, it's all about the odd nodes. So first off, we need to identify the odd nodes. So this one here has got 3 coming out of it, so that's an odd number. This one here has 3 coming out of it, so that's an odd number. This one has 3. And then this one has 5. So, Chinese postman. First of all, we've identified the odd nodes, but we are actually going to need to write those down and state them. So we have our odd nodes, and they are GA, SS, PP, and PA. So once we've got that information, we can start to pair them up. So we'll want our pairs. It is really useful being systematic at this point, so that we don't miss one. So if we start with GA, GA could go with SS, GA could go with PP, or GA could go with PA. So if this pair is used, then the other ones that we've got left over are PP and PA. If we're using this pair, then the other two we've got left over are going to be SS and PA. And if we've used these pair, then it's going to be these two that have been left over. So we've sorted out our pairs. From here, we then need to find out how far it is between them. Now, we've got some that are really helpful. So like SS to PP, they are really nice and close, and distance from there is going to be 5. In the last question that we did on Dijkstra, we actually worked out how far it would be from PP to GA, and that was 29. So if that is 29, we know that that is the quickest way to get from here to here. So this or this option, so this is actually going to be 29 as well. And then we've got other ones that we're actually going to need to work out. So GA to PA, if we went down this way, we've got 15 and 8 and 3. Our other option is 14 and 9, which is going to be shorter, so that would take us 25. So that's our first one that we've worked out, and that's coming in at 30. Nine and 40, not 25, 23. So that's coming in at 28. Then we've got SS to PA. So we could do it as 5, 3 and 7, which is 15. And that one looks the shortest way. Or we've then also got to work out GA to PP. No. Ah, that's because I wrote it in the wrong place. That one's 15. And then PP to PA, we've got 4 and 3 and 7, so that one's going to come in at 14. So, although just from looking at it right at the beginning, given this is 28, we know that these are going to be bigger, you still have to write it out. So we've got 44 here and 43 here. So this one's going to be our smallest. We do actually have to label it as being our smallest. And then from there, we have our Chinese postman problem, and that equals the total time for all of the roads, which was 188, add on the shortest one, which was 28, and that should hopefully give us 216. And that was in minutes. Unless they tell you otherwise, it's not a problem leaving it in minutes. They may ask you for it in hours and minutes, but converting it shouldn't be too much of a problem. Okay, and then we've got part B. So in discussion with the group, they don't mind where they finish. So that's going to be a different start and finish. So we have started at the Galleria. So we have started at GA. So we've got a start at GA. We've got a finish. And we've got a pair. So, looking at these values here, we are looking for the smallest pair that we could get. So the smallest pair that we've got is 5. So if that is 5, then the pair that gives us that is SSPP. So the only one we've got left over has got to give us our finish point. So we will finish at PA. So the length of our Chinese postman problem for a different start and finish is the total of all of the roads plus the shortest repeat. So this is the pair that we're repeating. So from here, that's going to give us 193 minutes. So by the mere fact that they don't have to walk all the way back up to where they started, as a tour guide, it's kind of reasonable that they might want to have an explore themselves, but it does cut down their actual tour by 23 minutes. Okay, so section D. This is also based around Florence. And this is looking at travelling salesmen. So, on table 1, use nearest neighbour algorithm starting at AB, or BA even. And we're doing this for an upper bound. So, nearest neighbour, we are told we start at BA, and then we are going to travel. So, looking down BA, the closest thing there is MF, and that is 1 minute away. So, from MF, can't go back to BA yet, closest thing, so nearest thing for nearest neighbour, we're going to be going to BP, and BP is 8. So we're now at BP. We can't go back to BA, we can't go back to MF, but actually the nearest thing we've got is PA, so we'll go there, and that will take us 3. Then from PA, the only place we've got left to go is SC. So PA to SC is 8. Then this is a tour, so you have to go back home. So at the end, you're going to need to go back to BA. Now, inconveniently, there isn't a direct route from SC to BA. But the shortest way to go from SC to BA is to go to MF and then go to BA. So that one actually comes in at 15. So that's going to be written as BA 1 MF 8 BP 3 PA 8 SC 15 BA. So the key things that they're going to be looking for is that you've gone to every single one and that you went back home at the end. And they are looking at finding the best upper bounds, so you are going to have to add these together as well. So AA is 16, plus 4 is 20, so looking at 35. So on the second one, it's asking us to use prims to find a minimum spanning tree. So a minimum spanning tree is going to be everything connected but done in a really specific order. So for prims, if we start in the first column, so put a 1 at the top of that, highlight it and cross it out, then we look for the smallest thing in the highlighted column, circle it, write it down. So we have MF BP is 8. Put BP as the second thing we've chosen. So we've got these two columns highlighted, so we can choose anything from these two columns. The smallest thing in there is this 3, so that came from BP PA, and that was 3, so we've now added PA into our tree and we've crossed out BP. We're now looking for the smallest thing from any of these 3. In this case it's this 7, so we've got SC goes to BP and that's 7, cross that out, stick a 4 at the top. It is important that you've got the circles, it is important that you've got the crossing out because that's what they're marking you on. Sometimes they want you to draw the minimum spanning tree, not always, but it's worth doing because it doesn't really take very long. So you've got MF goes to BP, BP goes to PA, and SC came from BP. So this bit's your minimum spanning tree. These guys added together is going to give you 18. So this is our minimum spanning tree. Then it says hence find a lower bound. Hence, in exam term, basically just means use something you've already done to do the next bit. So finding your lower bound. Lower bound, what you need to notice is that between table 1 and table 2, BA has disappeared. So to add in BA, we are going to put in BA with 2 of its links. So the smallest one is to MF, and then there's going to be a second link. Now that second link is going to be the next smallest. In this case, there's 2 9s, so it doesn't matter which 9 you choose, so long as you've got one of them. So your lower bound is going to be 1 plus 9 is 10, and then 10 plus 18 is 28. So you've used your part B to get your lower bound. So we have a lower bound at 28 and we have an upper bound at the 35. So for part C, given the minimum time is T, use your answers to write down the smallest interval. So lower bound is 28. T has got to be somewhere between your lower bound and your upper bound. And if you think about inequalities, the big end of your inequality is always going to go to the biggest end of the numbers, the littlest end to the littlest end of the numbers. So you end up with effectively a mark for having the 28 less than and another mark for this less than 35.